In this chapter, Chapter 9, titled Linear Momentum and Collisions, we study the concept of impulse and momentum. And just as we link the concept of work with kinetic energy in Chapter 7, we'll be able to do so in this chapter with impulse and momentum. Another analogy that we'll compare with Chapter 7 and 8 is that of a conservation law. In Chapter 7 and 8, we said that in the absence of non-conservative forces doing work on our system, its mechanical energy is conserved. In this chapter, we say that in the absence of external forces delivering an impulse in our system, its momentum is conserved. Indeed, we can argue that Newton's laws of motion are the direct result of conservation of momentum. Let's begin by introducing momentum. First, let us say that the momentum we study in this chapter is linear. Anytime an object is moving, it has momentum and, of course, kinetic energy. However, we distinguish the momentum that an object will have in this chapter as being linear if its motion is linear rather than rotational. The abbreviation for linear momentum is the small letter p. It is a vector and its units are the kilogram meter per second. Here again, momentum p is the product of mass times velocity. And as we just said, it is a vector because velocity is a vector and we're merely multiplying it by the scalar mass. And as a vector, of course, we're faced with breaking down the vector into components, and we limit our dimensionality to 2 dimensions in the xy plane. If we are to define a system that is made up of 2 objects, then we can talk about the total momentum of the system being made up of the sum of the individual momenta, object 1 and object 2. Here again, we consider the components in the x and the y direction. In fact, we can rewrite Newton's second law in terms of momentum. Let's take the case where mass, the mass of the system or the object, remains constant. In this case, we rewrite acceleration as the derivative of velocity over time. And because mass is a constant, we can place it within the derivative, since if we take the derivative of momentum, mass is a constant and just merely gets multiplied by the value of the derivative of v. And so we can say that force, Newton's second law of motion, force produces a change in an object's momentum, a time rate of change in an object's momentum. Let's view an animation regarding momentum.
When one mass collides with another mass that is twice as great, each bounces away from the collision. The vectors represent the products of the mass and velocity of each object. These products are the individual momenta of the 2 objects.
So in this case, our system is made up of mass 1 and mass 2, and this would be an example of the total momentum of the system being made up of the sum of the momentum of object 1 added to the momentum of object 2. A little later in this chapter, we'll be able to talk about collisions and see how 2 objects that undergo a collision interact with one another and what we can say about their total momentum. But before we do that, let's introduce yet another term, that is impulse. Impulse abbreviated by the letter I, with the same units of momentum, the kilogram times the meter per second. Now, of course, this can also be written as the Newton multiplied by a second, as we will see very shortly. These two units are entirely equivalent because the Newton is the kilogram meter per second squared, but if we multiply that by a second, we get the kilogram meter per second. Impulse is the product of force times time. And here in this integral form, what we are referring to is the force at every instant in time that is exerted on an object for the amount of time that the force is in contact with the object. We can also define impulse as the average force that is exerted on an object multiplied by the time interval of that contact time. Just as we saw in Chapter 7, work could also be determined, and that was the value of the integral of work, force, dotted with displacement, could be determined by taking the area under the graph of force bounded by the horizontal, which in this case is time. Here, this is also true. If we consider the average force, what we see here, average force in this diagram has a bar over it. The area that would be approximated would be the area of the rectangle, which is shaded here under the curve of the instantaneous value of force. So whether we obtain impulse through the integral of force times time, the area under the curve, or the average force times an increment of time, they are entirely equivalent. It's just that we have several methods available to us. Now, in Chapter 7, if you recall, we said that whenever a force acts on an object while it is being displaced, energy is going to be transferred. It could either be an increase in energy or decrease, and specifically it was kinetic energy that we were referring to. We were able to derive the work kinetic energy theorem in that case, and here we are going to make a similar derivation of impulse momentum theorem. We start out with force equals derivative of momentum over time, which we saw earlier can express Newton's second law. We rearrange the terms so that we have dp equals f dt. Take an integral of both sides. The integral on the left of dp becomes delta p. The integral on the right, f dt, is merely impulse, the definition of impulse for instantaneous force. And so here we can see that impulse and change in momentum are entirely equivalent. In other words, this is known as the impulse momentum theorem. If a force acts on an object, and let's just for the time being say that it's an average force over an increment of time, so that we are using this definition of impulse, the result is the object's momentum will change. It might increase, it might decrease, or it might merely change in direction, because here we have to be careful. The fact that impulse and momentum are both vectors, just as velocity can, as a vector, can change either in direction or in magnitude, here momentum can change in either magnitude or direction. So whereas in the work kinetic energy theorem we didn't have to consider the directional form since we were dealing with scalars, in this case we do. Now, impulse is readily visible in almost any form of contact sport, because in a contact sport, a force is in contact with an object over an increment of time, however minuscule that might be. Here, for example, the foot on the soccer ball. Here, for example, the bat on the baseball, the racket on the tennis ball, the fist on the face, or the golf club on the golf ball. And I've listed below a table that has typical values of average force for different sports, as well as typical values of contact time in milliseconds, of course. And I threw in there the masses of the objects, the baseball, the football, etc., so that one could sort of get an idea of the changes in momentum that these objects would undergo as a result of having an impulse delivered to them. How about the car that has a collision with either another car or, in this case, a wall? By Newton's third law, the car strikes the wall strikes the car back with a force of equal magnitude, of course opposite in direction. This force is on the car. And if we consider the amount of contact time for which this force is delivered, we can certainly see that there will be a change in the momentum of the car. So impulse and momentum is certainly associated with auto crashes as well. But let's now shift gears a little bit, and since we have started talking about collisions, let's follow through with that. Specifically, Newton's third law. In this case, we have a golf club and a golf ball. If we were to isolate the golf club and the golf ball as two objects comprising a system, rather than the golf club being a force that acts on the ball over an increment of time. In other words, let's introduce the golf club, which previously was the agent of our force, as a member of a two-object system. By Newton's third law, the club exerts a force on the ball exerts an equal but oppositely directed force on the club. The forces being equal but opposite in direction, we can write force of club on ball equals force of ball on club in the opposite direction. Rearrange the terms and write them up, m2a2 plus m1a1, of course using the form of Newton's second law in terms of momentum, the derivative of m2v2 with respect to time plus the derivative of m1v1 with respect to time equals 0. And of course that is the derivative of momentum of the second object with respect to time plus the momentum of the first object with respect to time equaling 0. Well, this just implies that there is no change in the object's in the system of two objects' momentum. In other words, the total momentum of the system undergoes no change in time. And that can only be the case if the momentum of the system is constant. And this, in fact, will be our premise for the next section that deals with collisions. That is, we eliminate external forces and include all interacting objects to within the system so that the momentum of the system will remain constant. But first, let's view an animation related to conservation of momentum.
Conservation of momentum follows from Newton's third law. Because the force of body 1 on body 2 is equal and opposite to the force of body 2 on body 1, the sum of the forces acting on the bodies in the system is always 0. The total momentum of the system, m1v1 plus m2v2, does not change in time. Physicists believe that the momentum is always conserved.
Well, what that is going to mean is that in the next section where we examine collisions between objects, we will allow the system to be isolated so that there are no forces acting on the system except within the members of the system. And so we'll consider two particles colliding with each other and the fact that the momentum of the system of the objects must remain constant. Okay, so the first thing we want to say is that in any type of collision, the total momentum of the system is always conserved. And what that means is that if we add the initial momenta of the system, we should, the sum should equal the final momenta of the system. And if we replace the terms P initial 1, P initial 2, P final 1, P final 2 with the form of the definition of momentum, which is mass times velocity, we get this term. So this is true for any type of collision. Now, the fact that we are saying that type implies that there are more than one. In fact, we classify two types of collision. Collisions which are said to be inelastic, and in this case, all collisions, for the most part, where contact is made between the two objects fall into this category, inelastic collisions. They do conserve momentum, but of course there is contact between the two objects. If, however, there is no physical contact between the two colliding objects, we say the collision is elastic in nature. It's a type of elastic collision. And a little later we'll elaborate exactly what the difference between those two types of collision are. But let's view an animation that will allow us to examine these two types of collision. So we start out with the inelastic collision where contact is made. Here, object 1 has a speed of 10 meters per second to the right. Object 2 is at rest. These little arrows indicate the direction of motion that the objects will take after the collision. So we have before collision, object 1 has a velocity 10 meters per second to the right. Object 2 has initial velocity of 0. After the collision, you can see now the final velocity of ball 1 is 0, but ball 2 has a velocity of 10 meters per second to the right. And if we want to adjust the value of 2 so that we can see what happens if we have a head-on collision, so object 2 now has a velocity of minus 10 meters per second, we can see after the collision there is almost an interchange between the velocities. Now ball 1 has a velocity of minus 10 meters per second, ball 2 has a velocity of 10 meters per second. How about if we increase the velocity of ball 1? This case, again, we see that there is almost an interchange between the velocities. And by the way, we're assuming that both balls have the same mass. Now let's consider the other type of collision, the elastic collision, where no contact is actually made. And you might ask yourself, how can two objects collide if they never make contact with each other? Well, the term collision really refers to the interaction that two objects exert on one another. And the interaction means the forces that they exert on one another. In this case, we have a helium nucleus, for example, let's say 2 protons within the nucleus, no electrons, so this is a doubly ionized helium nucleus. And here we have a singly ionized nucleus, for example, hydrogen, no electron, and in physics 2, we would study the fact that these two exert repulsive forces uh, on one another because they both have the same charge. And so let's see what a collision event between these objects might look like. They seem to be approaching one another. No contact is made, but the repulsive force causes them to move in the opposite direction so that they never actually make contact with one another. And we can increase the initial speed of the objects, here 2 million meters per second. And we can see that, again, no contact is made. It's just that the motion is, or the collision event occurs more rapidly. If we increase the distance between the objects, again, no contact is made, and there's a minimum distance where a line would join the two objects. Okay, well, we're ready to investigate different types of collisions. And here we're going to quantify methods for calculating final velocities, provided we know the initial velocities, or conversely, if we know the final velocities, being able to calculate the initial velocities. Now, an elastic collision in one dimension is a collision where, again, no contact is made. Momentum is, of course, conserved, as it is in any type of collision, but there is something else which is conserved in the system, and that is the kinetic energy of the system. So the kinetic energy of the objects prior to the collision, the sum, should equal the sum of the kinetic energy of the objects after the collision. So we basically have two equations, and if we assume that we have two unknowns, V1 final, V2 final, to use these two equations to solve for the two unknowns means that we would use substitution of one term onto another. The algebra is hideous. In fact, our book shows us the derivation of the terms, but here I will just give them to you. It basically works out that V1 final is related to V1 initial and V2 initial in this form, and V2 final is again related to V1 initial and V2 initial in this form. One other thing that we need to say about conservation of kinetic energy, what it really means is that there should be no change in the kinetic energy of the system, so that if we are asked how much kinetic energy was lost in the system during the collision, or possibly gained, if that might be the case, the answer would be none. Now, does this mean that the system has no kinetic energy? Well, no, not at all. It just means that the kinetic energy the system had prior to the collision is exactly equal to that which it has after the collision. And so here we have M1, M2 approaching one another in a head-on collision. Here, of course, the masses are not equal, and we can see that after the collision, M1 and M2 have their respective velocities. Now, are there such things as elastic collisions in the real world? The answer is only in the atomic world. For us, any collision, the very idea of a collision means that there has to be contact between two objects, or three or more. In other words, we eliminate the fact that one object cannot have a collision with itself, but secondly, the term collision implies that in our everyday language that contact is made. So what we're saying here, if we're referring to elastic collisions, what we're really referring to is atomic nuclei. In this book, that seems to be outside the scope of the work that we do. We don't deal with atomic physics. So what we're going to do when we label a collision to be elastic in nature, we are going to basically idealize a situation in which so little kinetic energy is lost that for all intents and purposes, like we neglected friction, for example, in our moving projectiles, etc., we are going to say, yes, this is labeled as an elastic collision because we are neglecting the small losses in kinetic energy. Anyhow, here's another animation. We have a 5-kilogram ball uh, which will collide with another 5-kilogram ball. The initial velocity of ball 1 is 10 meters per second to the right. The initial velocity of ball 2 is 0. And let's see the collision event. Keep in mind, even if we see the contact, we are working within the realm of the very idealized situation in which we can say kinetic energy is conserved. Notice that if the masses of the two balls are equal, there is merely a transfer of velocity between one object and the next. How about if we increase the mass of object 2 to double its value to 10 kilograms? Let's now see what happens to the final velocities. Still keeping ball 2 at rest. We can see that now we don't have a transfer of velocities, but the final velocities are distributed among the two balls. And of course, we would calculate this using the equations in our slide, in our previous slide. Okay, how about if we assign an initial velocity, and we'll start with the minus 10 to ball 2, and view at twice the mass what happens to the final velocities. Here you can see that ball 1 exits from this collision event with a much greater velocity than ball 2. Now if we increase the mass of ball 2 to 20, let's see what happens. Here you can see that each with the increase in mass, or subsequently an increase in velocity going from 0 to minus 10, the final velocity of ball 1 increases and increases and increases, and we can say that barring any loss of energy, when a light object collides with a very heavy object, the velocity of the lighter object will be significantly larger than that of the heavy object, and the velocity of the heavy object may actually not be even detectable, notably detectable. Let's view this video animation for elastic collisions.
When two moving objects of equal mass undergo an elastic collision in one dimension, the particles exchange velocities. Although the momentum and kinetic energy of each particle changes, the momentum and kinetic energy of both particles taken together is the same before and after the collision.
So this again emphasizes the nature of this form of collision. The other type of collision which we talked about is the inelastic collision. Once again, momentum is conserved as it is in any collision. But this time, we say that there is a change in the kinetic energy of the system, and very often that involves a loss in kinetic energy of the system, so that the final kinetic energy of the system does not equal the initial kinetic energy, and most often is smaller than the initial kinetic energy. So one might ask, where does the energy go? Well, if you recall, we said that an inelastic collision involves contact. When contact is made between two objects, very often sound is heard. There is friction associated with the contact region. There might be some deformation at the contact region, and all of these processes involve energy transfer out of the system into the environment, for example. And so with this type of collision, that loss in kinetic energy is what we detect when we consider the change in the kinetic energy of the system. Now, there is one special case of the inelastic collision, and that is known as perfectly inelastic. And all that really means is that two objects collide with one another of initial momentum 1, initial momentum 2, but upon the collision event, they emerge so that their final velocities are exactly the same. And what that means is that the magnitude of their velocity is the same. In other words, they move at the same speed, and so is their direction. So you might say, how can that be? Aren't they supposed to move apart from one another? Well, this is the case where we might have, for example, a car rear-ending another car, and their bumpers lock in such a way that both cars move as a unit with a common velocity. Or the case of a train car colliding with another train car, for example, purposely if they're going to be linked, and so the collision event is the linking, which subsequently leads to both cars moving at the same speed. Let's view an animation of this type of collision. Here, 5 kilograms, 5 kilograms, 10, 0, we can see the collision both objects moving at the same speed following the collision. And in fact, you can see that that speed is half the initial speed that object 1 had because object 2 was not moving. Let's make object 2 move at minus 10 meters per second and keep the masses the same. This would be a head-on collision. Aha! No objects are moving following the collision, and of course we have to conserve momentum, and so because the momenta of object 1 plus object 2 added up to 0 initially, the final must also add up to 0. Well, let's see if we increase the mass of 2 to 10 kilograms and consider the collision event. You can see that the collision will take on, the velocity will be in the direction of the more massive object, but here again, both objects are moving at the same velocity in terms of magnitude. Okay, collisions in 2 dimensions. This is the case where we now consider the component portion of momentum. Here, if we restrict ourselves to inelastic collisions, since that gives us a much easier grasp of the situation, we have conservation of momentum in the x component of momentum, conservation of momentum in the y component of momentum, and if we allow the x and y components to be written in terms of the angles of the collision, then you can see that conservation of momentum can be written in terms of theta, theta 1 initial, theta 2 initial, because theta 1 initial multiplied by the magnitude v1 initial is nothing more than v1 initial in the x direction. Here, v2 initial times theta 2 initial is the x component of the second object's initial momentum, and so forth and so forth. Let's view some animations regarding these types of collision, and let's begin by viewing the video animation.
When a moving object undergoes an elastic collision in 2 dimensions with a stationary object with a different mass, the particles scatter off from each other. Momentum and kinetic energy are both conserved. Nevertheless, knowing the initial masses and velocities is not enough to determine the final state. In general, one must measure the outgoing angle or speed of one of the particles to calculate the remaining speeds and angles in the system.
So it becomes much more complicated, where here the initial angle theta 1 initial, theta 2 initial was 0 because both objects were along the x direction, but the outgoing angles are not. Now this animation, of course, is for elastic collision, which we have not added the term here. Here we have a diagram of two objects before the collision and the two objects after the collision, with a little animation that will play here. We have object 1, object 2, 10 kilograms, 10 kilograms. Initial speed of 1 is 10, initial speed of 2 is 0. And here, of course, if this is an inelastic collision, then it would be sufficient to use this equation with theta 1 initial, theta 2 initial as 0 in both the x and y direction, of course, and then we would calculate the final angles. Some inelastic collisions. Here, an astronaut is still, a book is approaching the astronaut, so the astronaut's initially at rest. The book is moving at 4 meters per second. This is a perfectly inelastic collision because both astronaut and book move with the same common final velocity. So it's as though we now have the combination of the masses, 63 kilograms, moving at some v final. Here, another situation, the locking of the bumpers, moving as a unit. And here we have an extreme of the inelastic, a bullet striking an apple. Of course, this is the moment before the apple disintegrates. A lot, tremendous amount of energy loss here, very inelastic collision. Most kinetic energy would be lost. This concludes the first part of Chapter 9. In Part 2, we will talk a little bit about rocket propulsion. Until